Alright, in this video I'll be solving the 9709 Pure Mathematics 3 paper 31 for May-June 2025. For copyright reasons, I will not be displaying the question paper, so make sure you have a copy with you to follow along. And before we get into the video, I just want to kindly ask that if you find the videos that we make on this channel useful, please subscribe. It means a lot. I know it may not mean much to you, but it means a lot. And it's an indicator to us that you're finding the content that we're making helpful. So we should create more and better content. So if you do find the videos useful, please subscribe. Thank you. Question number 1. Sketch the graph of y is equal to the modulus of 2x minus 3. Alright, so let's draw up our y-axis and our x-axis. So when you want to draw the graph of a modulus function, right, first draw the graph of the line, the straight line without the modulus. So if we want to draw the graph of a straight line, we need 2 points, right? So I can pick the point when x is 0. We know that y should be minus 3. And then I could also use the point when x is 1. So that would be 2 times 1 minus 3, which is minus 1. I don't like that point. I want one of them to at least be positive. So let's use x is 2. So when x is 2, we've got 2 times 2, 4 minus 3, 1. Okay. Now it's just that if we use 1 and minus 1, and I've got 0 and negative 3 with the scale that we have here, it's not going to look nice. So that's why I've picked 2 different points, but it would still work. It's just not good for illustration purposes. So let's mark our 2 points. We've got 0 and negative 3. 0 and negative 3. Negative 3 will be here, so let's mark that there. And then we want 1, 2. And we want 1 unit in the y-axis. So our other point will be over here. Okay. And then just draw a line through those 2 points. All right. So this is y is equal to 2x minus 3. Then the next thing to do is to reflect anything that's below the x-axis. So this part over here needs to be reflected. And if you reflect it, you should get something like this. See if we can rotate that to be flatter. Okay. And the equation of that arm should be y equals negative 2x minus 3. So just take this part, put it in brackets, and make it negative. And delete anything that's below the x-axis. Oh, I don't want to delete the negative 3. We need to mark this intercept here. Because we've reflected that used to be at minus 3, it comes to positive 3. Okay. And then we also need to figure out what the x value is. So make sure you've labeled all your intercepts. So in this case, we're saying when is 2x minus 3 equal to 0? 2x minus 3 is 0 when x is equal to 3 over 2. So this has to be x is 3 over 2. And that there is the graph of y equals modulus of 2x minus 3. For 1 mark. Oh, stingy. Part B. So part B says solve the inequality 3x minus 1 is less than our modulus function from part A. All right. So because part A was sketch the graph of the modulus function, and then part B is solve the inequality, they're trying to lead you to use the graphical method of solving your inequality. Because of course you could do this algebraically, but just because they forced you to sketch the graph, it will be easier to just follow the graphical method. Which means what we have to do is we already have a sketch of the modulus function. We need to draw this line on the same graph. So we want to draw the line y equals 3x minus 1. This is just a straight line, so we need 2 points that lie on that line. And so we can pick the point when x is 0. We've got -1. And we can pick the point when x is 1. We'd have 3 minus 1, so 2. Okay. So we've got 0, -1, which is there. And then we've got 1 and +2. So +2 would be 1 and +2. That's there. Okay. And if we draw a line through the 2 points, should look something like this. All right. And be careful with your gradients, because I can tell my line here, 3x, must have a steeper gradient than my modulus function, right? So it means that this green line has to be steeper than the red line. It can't be flatter than the red line. If it's flatter than the red line, you'd end up with something like this. That would actually intersect the modulus function 2 times. But our gradient here is 3, which is bigger than 2. So the green line has to be steeper than the red line. Okay. And so that means we only have one point of intersection. And so the lines that are intersecting there are this green line, which has equation y equals 3x minus 1, as well as this red line. So if we want to find that point of intersection, this one here, we have to solve these two equations simultaneously. So we've got y is equal to -2x minus 3, and we've got y is equal to 3x minus 1. So we can just equate the two together. So -2x minus 3 is equal to 3x minus 1. And so if we just expand the bracket on the left there, we've got -2x plus 3 is equal to 3x minus 1. Then let's move the -2x that side, so that it's 3x plus 2x, and move the -1 to the other side, so we've got 3 plus 1, so 5x is equal to 4. 5 both sides by 5, and x is 4/5. So that means the point of intersection there is at 4/5. Now that we know what our point of intersection is, we have to solve the actual inequality. I'm just going to rewrite the inequality. I want to color code it so that we can compare. So inequality is 3x minus 1 is less than modulus of 2x minus 3. So the question is asking, when is the green line below or less than the red line? When is the green line below the red line? So we know that the cutoff point is going to be at 4/5. So are we taking the region to the left of 4/5 or to the right of 4/5? If I pick, for example, let's say x is somewhere here, which looks like it's greater than 2. If I pick a point here, I hope you can see that the green line is actually above the red line. So in this case, that doesn't actually match what we're looking for, because we want the green line to be below the red line. But if we pick a point on the other side of 4/5, so maybe somewhere here, we can tell that our green line is actually below the red line. So we want every point that is to the left of 4/5, because if I pick any point there, I can tell that my green line is always below the red line. And so we can conclude that it has to be to the left of 4/5, or in other words, x has to be less than 4/5. And that's our final answer. Question number 2. It is given that 2 ln p plus ln p minus 1 minus 1/2 ln q plus 1 is equal to 3. Find q in terms of p. So we're solving for q. Okay, so let's keep that in mind. The first step when you want to solve a logarithmic equation is you want to combine all the logarithms into one, right? But for us to be able to combine all the logarithms into one, they must all have the same coefficient. So this has a coefficient of 2, this has a coefficient of 1, this has a coefficient of half. We need to change it so that all of them have a coefficient of 1. And we can do that using the law of logarithms that says ln a to the n is equal to n ln a, except we want to use it in that direction because we want to take the coefficient and write it as a power. So we'll do that for 2 ln p, it becomes ln p squared, plus the second term is fine, ln p minus 1, minus, I want to take the half up, so ln, alternatively you could also take the half up with the negative sign. It's just really a matter of preference. I'll keep the negative sign down. We take the half up, and this is all equal to 3. Once it's like this, we want to use our laws of logarithms. So we have ln AB is equal to ln A plus ln B, and we have ln A over B is equal to ln A minus ln B. So let's start by using this law of logarithms on the first two terms there. So that becomes ln p squared multiplied by p minus 1 minus the ln q plus 1 to the half is equal to 3. Okay. In fact, I think I'm just going to write this as, instead of writing it as the power half, I'll write it as a square root. So ln square root q plus 1, like that. Okay, and then now we're going to use the second law of logarithms because we've got ln a minus ln b, and we want to combine that. So that becomes ln of this, which is our ap squared times p minus 1, and our b, which is the square root of q plus 1. And this is all equal to 3. Now that we've combined all our logarithms into one, we can now apply the exponential function on both sides because the exponential function will cancel out the ln. So we're going to say e to the power of all of this is equal to e to the power of 3. So the e will cancel out the ln, and we end up with p squared times p minus 1 over the square root of q plus 1, and this is equal to e to the 3. Right? And now remember that we are solving for q in terms of p. So that means our goal is to make q subject of the formula. So let's multiply both sides by root q plus 1 because we want to get q out of the denominator. So that becomes p squared times p minus 1 is equal to e cubed times our square root of q plus 1. And now let's divide both sides by e cubed because again the goal is to isolate that q. So divide both sides by e cubed. You've got p squared times p minus 1 over the e cubed is equal to the square root of q plus 1. And now square both sides to get rid of the square root. So now I've got this p squared multiplying p minus 1 over e cubed, and this is all squared. This is equal to q plus 1. Now just subtract both sides, subtract 1 from both sides to isolate the q. So you've got q is equal to p squared times p minus 1 over e cubed, and this is all squared minus 1. And that there is q in terms of p. Question number 3. Find the complex numbers of z for which z plus 5i over z minus 5 is real, and the modulus of z is equal to the square root of 17. Give your answers in the form z is equal to x plus iy, okay, where x and y are real. So for this question, it's a 6-mark question as well. Oh, nice. So for this question, what we want to do is obviously solve for x and y. The way we're going to do that is we need to create two equations that we're going to solve simultaneously. So the first equation is going to come from here, and the second equation is going to come from here. So let's start with the first equation because that one is a bit easier. We know that to get the modulus of z, the modulus of z is just the square root of x squared plus y squared. So that means I can say that the modulus of z, which is the square root of x squared plus y squared, is equal to the square root of 17. So if we square both sides, we have that x plus y squared is equal to, the square root is gone now, so it's equal to 17. That's our first equation in terms of x and y. Now we need to come up with another equation in x and y that we can use to help us solve simultaneously. So we're also told that z plus 5i over z minus 5 is real. So if they're telling us that this is real, this means that we can write it like this. Z plus 5i over z minus 5 is equal to the real part, and the imaginary part is going to be equal to 0. Right? We've got some real part, we don't actually know what that is, and the imaginary part is 0. So what we can do is to try to figure out what is the imaginary part of this thing in terms of x and y. And we know that whatever result we get from the left should be equal to the 0 that we get there. Since this thing is real, its imaginary part has to be equal to 0. So remember that z is equal to x plus iy, right? So I can rewrite that part with z as x plus iy plus 5i, and this is over z is x plus iy minus 5. Okay, for now I'm not going to include the right hand side. We'll come back to this once we've simplified this a bit more. And then I want to group the real part together, and the imaginary part should be separate from the real part. So in our numerator, we've got x plus, we can factor out the I, so that it's y plus 5. And in our denominator, we've got x plus, or rather x minus 5, because that's also real. And then the imaginary part is the iy. And we want to find a way to rewrite this in the Cartesian form, i.e. in the form x plus, let's not say x plus iy, but in the form a plus ib, right? Like this, so I can clearly see that this is my real part, this is my imaginary part. That's what we're trying to get to. Because when we get to that stage, I know that whatever my imaginary part is going to be equal to 0. So this is just the idea of dividing two complex numbers. If you're dividing two complex numbers, you have to multiply both the numerator and the denominator by the complex conjugate of your denominator, right? So the complex conjugate, if you've got a plus ib, your complex conjugate is a minus ib. So in our case, we want the complex conjugate of our denominator. So this is the real part, this is the imaginary part. So you have to change that sign there. So it has to be times x minus 5 minus, that becomes the conjugate. And we also multiply the numerator, x minus 5 minus iy. Let's erase this. And then we simplify. So I've got this x multiplying, I'm going to put a bracket on the x minus 5. I've got this x multiplying the x minus 5 bracket. So x times x minus 5. And then I've got the x multiplying the minus iy. So I've got minus xyi. And now I've got this imaginary part, I times y plus 5, multiplying the x minus 5 bracket. So I've got I, y plus 5, multiplying the x minus 5 bracket. And then I've got again the imaginary part, the I times y plus 5, multiplying the negative iy. So I've got negative I squared y multiplying the y plus 5. All right. and this is all being divided by. In the denominator, note that we've got a difference of 2 squares, right? Remember, if you have anything of the form a plus b times a minus b, this is a difference of 2 squares. It becomes a squared minus b squared. So in our case, we can say a is x minus 5 and b is the iy. So I hope you can see that this is a plus b times a minus b. So this should just simplify to a squared minus b squared, which should just be x minus 5 squared minus iy squared, right? So that's what we have on the, in fact, we can simplify it further. That's what we have on the denominator. So if we expand this, that's x squared. Let's keep it in red. That's x squared, 2 times x times negative 5, negative 10x. And then we've got 5 squared, so 25, minus square the I, square the y. Okay. But keep in mind that I squared is equal to negative 1. So that means this has to become positive y squared. And so that there is our denominator. It's x squared minus 10x plus 25 plus y squared. And also because we've said that I squared is negative 1, we can apply it here so that that part becomes a positive sign. All right. And now remember that all that we are interested in is the imaginary part. Because at the beginning of all of this, we say that our imaginary part has to be 0 since we're told that this whole thing is real. If it's real, it can't have an imaginary part. Our imaginary part is going to come from wherever we've got an I, which is this block over here. That's what's going to form our imaginary part. So we can say that that block, negative xy I plus I times y plus 5 times x minus 5. Here, if you want to, you can also divide it by the denominator, right? But it's not going to make a difference because we want to equate this to 0. If we equate this to 0, we know that our denominator can't be 0. So we end up just solving the numerator and equating the numerator to 0. So you can ignore the denominator here. So you get that this has to be equal to 0i, right? Because this is the imaginary part, and because this part is real, then the imaginary part has to be equal to 0. And so we can actually just ignore the i's since they're common on both sides. And this becomes our second equation. The first one was the x squared plus y squared is 17. X squared plus y squared is 17. And so now what we need to do is we need to solve these two equations simultaneously. I think let's expand this first equation. So negative xy plus y times x, that gives us xy, y times negative 5, that's negative 5y, 5 times x, that's 5x, 5 times negative 5, that's negative 25, and this is equal to 0. So we have that the xy's cancel out, and we've got 5x minus 5y is equal to 25. And so now I think let's make x subject of the formula here. It looks like it should be nicer that way. So 5x is equal to 25 plus 5y, divide through by 5. And so x is equal to 25 over 5, that's 5, plus 5y over 5, that's y. All right. And so we can now substitute our x here with 5 plus y. So that becomes 5 plus y, and that's squared, plus y squared is equal to 17. And now we can expand, so square the 5, that's 25, plus 2 times 5 times y, that's 10y, square the y, that's y squared, plus this y squared, and this is equal to 17. So 25 plus 10y plus y squared plus y squared, 2y squared is equal to 17. Let's write it in descending powers of y, so 2y squared plus 10y. Then I've got 25, bring the 17 this side, it subtracts, so it becomes 25 minus 17, which is 8, is equal to 0. Divide through by 2, y squared plus 5y plus 4 is 0. Factorize. So factors of 4 that add up to 5, that's plus 4 plus 1. So you get either y is negative 1 or y is negative 4. All right. And so those are the values for y. We can come back here to evaluate what x has to be. So we've got at y is negative 1. We have that x has to be 5 minus, or just minus 1. X has to be 4. And then at y is negative 4, we have that x is equal to 5 minus 4. So x has to be 1. So that means the solutions for z, we've got two of them. Either z is 4, because remember z is of the form x plus iy. Either z is 4 minus 1 times I, so 4 minus I, or z is equal to 1 minus 4 times I. And that there is our final answer for number 3. It's quite a long question, to be fair, but it's worth it, 6 marks. Let's go on to question number 4. The parametric equations of a curve are x is equal to e to the tan t and y is equal to 3 tan squared t. Find the equation of the tangent to the curve at the point E3. Give your answer in the form y equals mx plus c, where m and c are exact. Okay. So we want the equation of the tangent to the curve. The tangent is a straight line, so if you want the equation of a straight line, you need 1 its gradient and 2 a point that lies on that line. So we already have a point that lies on our tangent, which is the point E3. What we need is the gradient of the tangent to the curve. If you've got a curve and you want the gradient of the tangent at any point, you get that from dy dx. So that means we need to find what dy dx is for our parametric equations, and once we have dy dx, we'll be able to get the gradient of the tangent at our specific point. Once we have that gradient, we can use y equals mx plus c and get the equation of the tangent. So how do we find dy dx? We need to differentiate our parametric equations. Tan squared t. So let's start with x equals e to the tan t. Right? So we've got a function inside of a function. So we are looking for dx dt. So first, differentiate the outer function, which is the e. So if you differentiate e, you just get e. And multiply by, differentiate the inner function, and then multiply by its result. If you differentiate tan t, you get sec squared of t. And now let's move on to our dy dt. Again, we've got a similar thing. I'm going to rewrite this as tan t Let's put red brackets. Remember tan squared t is just the conventional way that we write our trig functions when they are raised to the power 2 or the power 3 or the power 4. We write the power first and then the t or the x or the theta, but it just means the same as tan t whole squared. So in this case, again, we've got a function inside the function. So the first thing is to differentiate the outer function, which is the one that's raised to the power 2. So first bring down the power 2 times 2, and we've got tan t, and then subtract 1 from the power. So 2 minus 1, that's 1. And now differentiate the inner function. So differentiate tan t. And again, if you differentiate tan t, you get sec squared t. And so we have that dy dt is equal to, this is 3 times 2, so 6 tan t sec squared t. Perfect. All right, so now we have dx dt and we have dy dt. If you want dy dx, that's going to be, we can create a chain rule here, right? We want to use dy dt and dx dt to find dy dx. So we can say dy dt multiplied by, we need a dx in the bottom, so I have to flip this. So multiplied by dt dx. And our chain rule is correct because that cancels out to give us dy dx. So that means dy dx is equal to, what is our dy dt? That's the 6 tan t sec squared t. And that's being multiplied by, flip this, remember this is all over 1. So this becomes 1 over, I'll write it as sec squared t e to the tan t. So we have that dy dx is equal to, here we can cancel out the sec squared t. And so we've got 6 tan t, and that's over e to the tan t. And this is our dy dx. Right. But notice here that we have a problem. Yes, we found dy dx, but we want to know what's our gradient at the point e3, i.e. when x is equal to e and when y is 3, what is dy dx? But our dy dx is in terms of t. So it means we need to figure out what the value of t is when x is e. So we can do that by using the equation, the parametric equation from the beginning. We know that x has to be equal to e tan t. So we know that x is equal to e to the tan t. Here we know that our x value is e. So we're saying that e has to be equal to e to the tan t. This is e to the 1. E to the 1 is equal to e to the tan t. So the bases are the same. So it means that the powers have to be same. So tan t has to be equal to 1. So t has to be equal to, that's arctan of 1. If you do arctan of 1, you're going to get a quarter pi. So that means our t here has to be a quarter pi. And so, in other words, when we're saying we want dy dx at x is e, we're saying we want dy dx at t is a quarter pi. So we can find dy dx when t is a quarter pi. That's going to be 6 tan of a quarter pi over e to the tan of a quarter pi. Tan of a quarter pi is 1, so we're looking at 6 times 1 over e to the 1, so 6 over e. So that means the gradient of the tangent to the curve at the point e3 is 6 over e. So now we have our gradient. M is equal to 6 over e. And we also know that a point that lies on the curve is the point e3. the point that lies on the tangent, rather, is the point E3. So we can use that to find our y-intercept. So we're saying when y is 3, m 6 over e, x is going to be e plus c. So 3 is equal to, the e's cancel out. So you get c is 3 minus 6, which is minus 3. And so therefore, the equation of the tangent has to be y is equal to 6 over ex minus 3. And that is the final answer. By the way, if you like the way that I break down questions and you're looking to get help with A-level maths, either just because you're struggling or you want to make sure that you get your dream grades, then you can sign up for tutoring by clicking the first link in the description down below. It will take you to my website where you can book a free discovery call with me so we can discuss how best I can assist you. The polynomial 3x cubed plus PAX squared, let me write it out. The polynomial 3x cubed plus PAX squared plus 7a squared x plus, there's a lot of unknowns, plus QA cubed is denoted by f of x, where p, q, and a are constants. A is not equal to 0 when f of x is divided by x plus 2a. Okay, so I'll write when f of x is divided by x plus 2a, remainder is negative 22a cubed. When f of x is divided by 3x minus a, the remainder is negative a cubed. Find the values of p and q. Okay. There is a lot of unknowns. Okay, so what we want to use here is the remainder theorem. And the remainder theorem states that if a polynomial, in this case f of x, is divided by x minus a, then p of a is equal to the remainder. Right, so if you divide f of x by x minus a, then p of, use p, I'm used to writing this theorem with p of x, f. Right, let's take that again. If a polynomial f of x is divided by x minus a, then f of a is equal to the remainder. So that means if x minus a divides our f of x here, then f of a is equal to whatever the remainder is. Okay, so applying that to what we have, and notice the value that you put in here is whatever makes this bracket equal to 0. So x minus a is equal to 0, x is equal to a. So we put a there. So if we apply that here, we're told that f of x is divided by x plus 2a, and the remainder is negative 22a cubed. So first we need to figure out what makes this bracket 0. And we can do that by doing x plus 2a is equal to 0. So x has to be negative 2a to make that bracket 0. So that means that by this theorem, f of the negative 2a has to be equal to the remainder, has to be equal to negative 22a cubed. Right? And we can apply that to the second line as well. So first figure out what makes that bracket 0. So 3x minus a is 0. So 3x is equal to a, and x is equal to a over 3. So that means by this theorem, f of a over 3 has to be equal to whatever the remainder is, which is negative a cubed. All right. And so now what we can do is to evaluate what's f of negative 2a using our function here. So you're going to go to the function, replace your x with negative 2a. So that's going to be 3 times negative 2a cubed plus pa times negative 2a squared plus 7a squared times negative 2a plus qa cubed. And we know that this is all equal to negative 22a cubed. Negative 22a cubed. Let's see if we can simplify this. So we've got 3 times, be careful with how you cube here. So make sure to cube the 2 first, the negative 2 rather. If you cube negative 2, you're going to get negative 8. Then cube the a, so you've got a cubed plus pa. Then square the negative 2, that gives you a 4. Square the a, that's a squared. Then here I've got negative 2a times 7a squared, so negative 14a cubed plus qa cubed is equal to negative 22a cubed. Let's simplify. 3 times negative 8a cubed, that's negative 24a cubed. Pa times 4a squared, so that is 4pa cubed. Negative 14a cubed plus qa cubed is equal to negative 22a cubed. All right. And so here I can simplify. I've got negative 24a cubed and negative 14a cubed. So what does that give us? That's negative 38a cubed plus 4pa cubed plus qa cubed is equal to negative 22a cubed. There's a lot of a cubes. Let's factor out a cubed on the left. A cubed negative 38 plus 4p plus q, and this is equal to negative 22a cubed. Now remember that in the stem of the question, we were told that a is not equal to 0. So that means I can just divide through by a cubed and it shouldn't be a problem. And the reason why I want to divide through by a cubed is I just want to get rid of it. I don't need it, right? So let's divide through by a cubed. If it was a possibility that a cubed would be, if there was a possibility that a could be 0, that would mean that there was a possibility of us dividing by 0, which we know is not allowed. So this only works because we're told that a cannot be 0. Okay. So we end up with negative 38 plus 4p plus q is equal to negative 22. And we can simplify this further. So I can write this as 4p plus q is equal to 38 minus 22, which is 16. Right? And we could even make q subject of the formula. Q is 16 minus 4p. And we can leave it here. And let's work with the other equation. So we also had that f of a over 3 is equal to negative a cubed. So that means we want to replace x here with our a over 3. Let me just zoom out for a second so we can see that. So that's 3 times a over 3 cubed plus pa times a over 3 squared plus 7a squared times a over 3 plus q a cubed, and this has to be equal to our negative a cubed. Okay. So now let's simplify this. Oh, my a looks like a 9. So 3 times cube the a, that's a cubed, over cube the 3, that's 27, plus pa, square the a, that's a squared, over square the 3, that's a 9. So I've got 7 being divided by 3, so 7 thirds, And then I've got a squared times a, so a cubed plus qa cubed is equal to negative a cubed. All right, so 3 over 27, that gives us 1 over 9, and that's a cubed plus, my a and my 9 look alike. So that's pa times a squared over 9, so that becomes p over 9a cubed plus 7/3 a cubed plus qa cubed is equal to negative a cubed. Here we can simplify 1 over 9 plus 7 over 3. What does that give us? That gives us 22 over 9 a cubed. 22 over 9 a cubed plus the p over 9 a cubed plus the q a cubed is equal to negative a cubed. I think I'm just going to multiply through by 9 to get rid of that denominator because I don't like it there. 22a cubed plus pa cubed plus 9qa cubed, and then that has to become negative 9a cubed. And now pretty much the same idea that we used last time, factor out the a cubed. That becomes 22 plus p plus 9q is equal to negative 9a cubed. Because a is not equal to 0, we can divide both sides by a cubed. And so we end up with 22 plus p plus 9q is equal to negative 9. And now we've got these two equations. I could probably simplify that one a bit. Write it as p plus 9q is equal to, take the 22 that side, this becomes negative 31. And now we have two equations here. We've already made q subject of the formula, so I can substitute this into here. So I've got p plus 9 times 16 minus 4p, and that's negative 31. So that's p plus 9 times 16, which is 144, and then 9 times negative 4, which is negative 36, and that's multiplying the p. This is equal to negative 31. So I've got p minus 36p, that's minus 35p, plus 144 is equal to negative 31. So if I move the negative 35p to the other side, I have 35p is equal to 144 plus 31, which is 175. Divide both sides by 35. This was a very long question. P is equal to 175 divided by 35. P is 5. If P is 5, then Q has to be 16 minus 4 times 5. So Q has to be 16 minus 20, which is minus 4. So we can conclude that therefore P is 5 and Q is negative 4. And that is our final answer. Question number 6. It is given that Z1 is equal to 3e to the quarter pi I. Z2 is equal to 3 over 2e to the 1/6 pi I. And omega is equal to 2e to the 1 over 2 pi I. And then part A, state the values of omega z1 and omega z2. Give your answers in the form REI theta, where r is greater than 0 and theta is between negative pi and pi. All right, so let's do that. Omega z1. So they're asking us to multiply this with this. So that's 2e to the half pi I, and that's multiplying the 3e to the a quarter pi I. Okay. So what you do is you just multiply the moduli. So you multiply the 2 and the 3, and then using your laws of indices, you know that this becomes e to the, you have to add your powers, because remember, x to the m multiplied by x to the n has to become x to the m plus n. This has to become, add this power to that power. So I've got a half pi I plus a quarter pi I. All right, so this becomes 6e. What is a half pi plus a quarter pi? That is 3/4 pi I. And that has to be omega z1. Now we need to find omega z2, which is going to be, what is omega? Omega is 2e to the half pi I, and this is multiplying z2, which is 3 over 2 e to the 1 over 6 pi I. And so again, same idea. You're going to multiply the moduli, so 2 times 3 over 2. And then we want to use laws of indices on the e there. So you're going to add your two powers, half pi I plus 1 over 6 pi I. And so I have omega z2 is equal to 2 times 3 over 2, which is just 3 e to the, add the two powers. So what is half pi plus 1 over 6 pi? That is 3 over 6 plus 1 over 6. So 4 over 6, so 2 over 3. 2 over 3 pi I. And so those are your two solutions, omega z1 and omega z2. Part B says, on a sketch of an Argand diagram with origin O, show the points A, B, C, and D representing the complex numbers z1, z2, omega z1, and omega z2 respectively. So A is going to be z1, B is going to be z2, and C is going to be omega z1, and D is going to be omega z2. Okay. So let's draw out our complex plane. So we've got the imaginary axis and we have the real axis. Okay, so the way we want to do this is, what is Z1? Z1, let me just copy the lineup. I don't need all of them. I need Z1, Z2. I need omega Z1. And I need omega Z2. Okay, so we want to start with Z1. And the way that we want to do this is to sketch these out using their argument and their modulus. So for Z1, the argument is a quarter pi, right? If you convert this to degrees, a quarter pi is 45 degrees. So it means that if I start from the positive real axis, I need to open up a 45-degree angle. So something like that. That's going to be a quarter pi. And I know that the modulus is 3 units. So I need to draw a line that is 3 units long, right? So this is going to be 3 units long, and that becomes point A. Okay. In Z2, what we're going to do is, what is our our argument is 1 over 6 pi. 1 over 6 pi is 30 degrees if you convert that to degrees. By the way, if you're not sure how to convert to degrees, if you've got an angle in radians, you have to multiply it by 180 over pi to get to degrees. So if you take your 1 over 6 pi, multiply it by 180 over pi, you get your 30 degrees. Okay, so in this case, we know that we are opening up an angle of 30 degrees. Make sure you're using your, I always mix this up. There's a protractor and a compass. Okay, make sure you're using your protractor to draw these angles, right? So we want to open up an angle of 30 degrees. I don't have a protractor, so I'm just going to estimate that this has to be roughly somewhere here. And I also know that my line here is 3 over 2, which is 1.5. So it has to be half of Z1. And the angle that I have, I don't know if we can show it. Let's put it there. It's getting cluttered. Just gonna point to it and say that that angle is a 6th pi. So that there has to be point B. And then let me change this color. We need a point C. So point C is omega Z1. So same idea, we want 3/4 pi. So 3/4 pi, that's 3 times a quarter pi. So 3 times 45, that's 135. So that has to be all the way over here. Let me get a straight line. Okay. And note that this line is 6 units long because the modulus there is 6. And I should have labeled the green line as well. That one has to be 1.5. There's a lot of clutter here. And finally, the last one has to be omega Z2. And the angle is 2/3 pi. So 2/3 pi, pi over 3 is 60 degrees. So this has to be 120. 120 would just be less than our pink line, which is 135. And this has got a modulus of 3. Okay. So these are our points A, B, C, and D. I should probably label. The green one has to be D. The pink one has to be C. And again, all we were doing is using our argument and our modulus. So the modulus is the length of the line, and the argument is the angle between the positive real axis and your complex number. Right. So that's part B. Part C says state the geometric effects of multiplying Z1 and Z2 by omega. Okay. So let's analyze our diagram here. What has happened? So if you look at Z1, Z1 is the point A, right? This is equal to Z1. And then what happened to A when we multiplied it by omega? So we're looking for omega Z1. Omega Z1 is point C. Omega Z1. So first, let's check the length of A. So initially, the length of A was 3. But when we multiplied it by omega, its length doubled in size. So it was stretched by 2 or enlarged by a scale factor of 2. So that's 1. And if we look at Z2 as well, if we're just looking at modulus, if we look at Z2, right, this is Z2. And then when it was multiplied by omega, notice that also the modulus of Z2, was 1.5. Then it doubled to 3 when it was multiplied by omega. So we can tell that the first effect that we're seeing here is there's an enlargement by scale factor 2, because the modulus seems to double when we multiply by omega, enlargement by scale factor 2. And then the next thing, if you look at A, clearly, how can we denote this? I'll use blue. So if you look at A started with an argument of a quarter pi, and then we added 90 degrees. In fact, I can show you that we're supposed to have a right angle here, right? We've rotated A anti-clockwise by pi over 2. So we've added pi over 2 to the argument of A, which has the effect of rotating A anti-clockwise by pi over 2. Right, so you took this A here. First, you enlarged it by 2, and then second, you rotated it by the pi over 2, and you ended up there. So let's undo that. Okay. And you can notice the same thing as well with B, with Z2. When we multiplied it by omega, again, we're going to have this right angle. I know it's cluttered, bear with me, but if you look at the red and the green lines, there's an angle of pi over 2. There's a right angle there. We first enlarged our B by 2, and then we rotated it by pi over 2 to get us there. Those are the two geometric effects. So whenever you add to the argument, it causes a rotation, right? Or when you multiply two complex numbers, it causes a rotation because you're adding to the argument. All right, so we've got a rotation, and we are going counterclockwise. Rotation by pi over 2, counterclockwise. Oh, anti-clockwise. That's right, anti-clockwise. And those are the two geometric effects of multiplying Z1 and Z2 by omega. Number 7, part A. Express 5 sine x plus 1 over 6 pi minus 4 cosine of x in the form r sine x minus alpha, where r is greater than 0 and alpha is between 0 and pi over 2. State the exact value of r and give the value of alpha correct to 3 decimal places. So for us to be able to do this, we need this equation that we have to be in the form a sine x plus b cos x. Once we have it in this form, then we can actually convert it to the r sine form. So that means I need to expand this because I can't have a compound angle for me to use the r sine form. I first need to simplify it. So I need to apply a compound angle formula for sine first to simplify that and get it into a form of a sine x plus b cos x. Then we can come back to the r sine idea. So if you go to the MF19, if you want to expand sine a plus b, you get that this is identical to sine a cos b plus cos b sine a. Not cos b sine a, cos a sine b. All right. And so let's use that on sine x plus 1 over 6 pi. Our a is x, our b is a sixth pi. So that's 5. Now put a big bracket. We've got sine a, so sine x, cos b, so cos a sixth pi, plus that's cos x and sine a sixth pi, and minus all 4 cos x. And we can evaluate cos 1 over 6 pi with the calculator. That gives us root 3 over 2. So we've got root 3 over 2, and it's multiplying the sine x, plus let's also evaluate sine 1 over 6 pi, which is a half. So we've got the half multiplying cosine of x. and minus our 4 cos x. So now multiply through by 5. So we get 5 root 3 over 2 sine x plus 5 times half, so 5 over 2 cos x minus the 4 cos x. And now let's simplify 5 over 2 cos x minus 4 cos x. So we've got 5 root 3 over 2 sine x. 5 over 2 minus 4 gives us negative 3 over 2. So negative 3 over 2 cos x. Alright. So now we've simplified this to that form we were talking about earlier, which is the form of a sine x plus b, or in this case, it's more of minus b cos x, which is exactly what we need to be able to use the r sine x minus alpha. So what we're going to do is I'm actually just going to equate this to our r sine x minus alpha, right? Because we're trying to find an equivalent way of writing this in terms of r sine x minus alpha. And then I want us to expand the right-hand side using compound angle formulas. Cos x is equal to, and we actually want to use the same compound angle formula, but this time it's negative. It's sine a minus b. Our a is x, our b is alpha. And so that becomes, going to factor out the r. So sine x cos alpha minus cos x sine alpha. And so we have 5 root 3 over 2 sine x minus 3 over 2 cos x is equal to, I'm going to multiply through by the r, and I want to actually swap the order so that here I write the cos alpha first, and here I also write the sine alpha before cos x. So r times cos alpha, and that's multiplying the sine x. I've got minus r times the sine alpha, and that's multiplying this cos x. In fact, I hope you can see that what I've put in red would be that's 5 root 3 over 2. So just by comparing the left and the right hand side, I get that r cos alpha has to be equal to 5 root 3 over 2, and r sine alpha has to be equal to 3 over 2. And we can use this to draw up a nice little right angle triangle. Okay, there we go. And so if I divide both sides by r there, I get that cos alpha has to be equal to 5 root 3 over 2r. And I know that cos is adjacent over hypotenuse. So if I put my alpha here, I know that my adjacent has to be 5 root 3, and my hypotenuse has to be 2r. And if I do the same with r sine alpha there, I divide both sides by r, I have that sine alpha has to be 3 over 2r, and I know sine is opposite over hypotenuse, and my opposite is going to be the 3. The hypotenuse is the 2r. Okay. And so from this triangle, we can now calculate what alpha has to be, and we can also calculate what r has to be. So let's start with r. According to Pythagoras, a squared plus b squared is c squared. And so in our case, we can say that 3 squared plus 5 root 3 squared is equal to 2r squared. And so 3 squared, that's 9, plus 5 squared, 25 times root 3. So times 3 is equal to, that's 4r squared. Okay, so on the left, we've got 9 plus 25 times 3. That's 84 is equal to 4r squared. So r squared is equal to 84 over 4, which is 21. So r has to be root 21. And then we need to find the alpha. We can just use SOHCAHTOA. Okay. So we can do opposite, which is 3, and adjacent, which is 5 root 3. So we can say tan of alpha is equal to opposite, which is 3, over the adjacent, which is 5 root 3. And so alpha has to be arctan of 3 over 5 root 3. So alpha is equal to, that is arctan of 3 over 5 root 3. And we are in radians. They want alpha correct to 3 decimal places, so 0.333. And so that's alpha, and that's r. And I know some of you are probably saying that that's way too long. So this is, I guess this is sort of the, if you're sort of deriving how to do these harmonic identities, this is the approach you take. But the formulas that you can memorize, I can't for the life of me remember the formulas, so I always end up just deriving it from scratch. But r, once you have it in the form a sine x minus b cos x, r is always going to be the same. R is easy. R is always going to be the square root of a squared plus b squared. So in our case, r is always going to be the square root of this squared plus this squared. So square root of 5 root 3 over 2 squared plus 3 over 2 squared, which is 5 root 3 over 2. Let's just double check that. That does give us root 21. 3 over 2 squared. Yes, it does give us root 21. So that's r. Same answer we got. Now alpha is the one that changes depending on whether it's r sine or r cos. If it's r sine, then you get that tan alpha has to be, what do we do down here? I can't remember. Sometimes it's a over b, sometimes it's b over a. So I'm trying to check which one this one is. This is 3 over 5 root 3. 3 over 5 root 3. So in this case, it has to be b over a, right? So the coefficient on cos divided by the coefficient on sine. That's how you get alpha. So this is when it is r sine. These are the two formulas you'd use. These, let me erase this part and that as well. These are the two formulas. You can just go straight to these formulas once you've made sure that your expression is in the form a sine x plus or minus b cos x. You can use these two for r sine x plus or minus alpha. Otherwise, if you're doing r cos x plus or minus alpha, then it means that the calculation for r is the same. It's always going to be root a squared plus b squared regardless. It's the tan alpha part. The tan alpha will be flipped, so it's a over b. So if you can remember these two formulas, then you can just go straight to the formula substitute. You don't have to go through everything that I've done. It's completely unnecessary, right? So just memorize these formulas and you should be golden. Or if you've got a short memory span like myself, then use your compound angle formulas to derive it from scratch. Get your triangle there, and then you can solve for alpha and r. But I do think for exam purposes, you're better off memorizing the formulas. And then we've got part B that says, hence solve the equation 5 sine 2 theta plus 1 over 6 pi minus 4 cosine of 2 theta is equal to root 7, for theta is between 0 and pi. Okay, give your answers correct to 2 decimal places. So what is the equation we started off with in part A? So this is the equation that we started off with in part A. And we showed that this equation can be written as, or we evaluated r and alpha. And remember, our task was to write this as r sine x minus alpha, which would mean that this is root 21 sine x minus, I probably should have done that at the end, concluded that this is root 21 sine of x minus 0.333 radians. Okay, 0.333 radians. So this is what we proved in the part A of the question. Notice that all they've done in the part B is where we had x, they've now put 2 theta. Where we had x, we now have 2 theta. So that means that if I want to model this, right, if I know that 5 sine x plus a 6 pi minus 4 cos x is equal to root 21 sine x minus 0.333, this means that I can just replace that x with 2 theta. So it means that 5 sine 2 theta plus 1 over 6 pi minus 4 cos 2 theta can be written as root 21. All that has changed is that the x has become 2 theta. 2 theta minus 0.333. Okay. So instead of using this, I can use this. And so I can say that root 21 sine of 2 theta minus 0.333 is equal to the square root of 7. Okay. And now we can solve. So divide both sides by the square root of 21. You've got sine theta, or not sine theta, sine of 2 theta minus 0.333 is equal to root 7 over root 21, which is root 3 over 3. And we want to do 2 theta minus 0.333 is equal to arcsine of root 3 over 3. Okay. And if we do that, we get 2 theta minus 0.333 is equal to, make sure your calculator is in radians. This is arcsine of root 3 over 3. That gives us 0.61548. Okay. And this value here that you get directly from your calculator is your principal value. This is the value that you're going to use to look for other solutions within the interval. So interval is theta has to be between 0 and pi inclusive. So if we want to check for other solutions, we're going to use this. And so let's do that. If we draw a sine graph, not a cosine graph, this here is going to be pi, and this is going to be 3 over 2 pi, and that is 2 pi. So that has to be pi over 2. Our solution there is 0.61. Pi over 2 is roughly 1.57. So 0.61 is to the left, maybe somewhere here, 0.615. So I can tell that I should have another solution somewhere here. By symmetry, if this distance here is 0.61, then that distance there has to be 0.615 as well. So if I want that solution there, that's just going to come from subtracting from pi. So I can say, remember, notice that my principal value is in terms of 2 theta minus 0.333. So even the solution that I get at this stage is of the form 2 theta minus 0.333. And this is equal to pi minus the 0.615. And so I have 2 theta minus 0.333 is equal to, let's simplify that, pi minus 0.615. I think I'll use just the 48 as well, just to make sure we are not rounding off prematurely. So 2.52611. And now we can simplify. So we're either getting a solution from here, or we're getting either a solution from here or from here, right? So we need to simplify both of them and solve for theta. So let's start with the left hand side here. 2 theta is equal to 2.52611. 2.52611 plus the 0.333. That gives us 2.85911. Divide both sides by 2. You get that theta has to be 1.42. Let's say to 2 decimal places, so 1.43 radians here. Then let's do the same here. 2 theta is equal to 0.61548 plus 0.33, which gives us 0.94848. Divide both sides by 2. We get that theta has to be 0.47. So we can conclude that therefore theta is 1.43 and 0.47 radians, correct to 2 decimal places. Question number 8. With respect to the origin, all the points A and B have position vectors. So OA has the position vector 2i plus 4k, and OB has the position vector 5i plus j plus 6k, respectively. The line L1 passes through the points A and B. Find a vector equation for the line L1. Okay. So remember, a vector equation of a straight line can be written in the form R is equal to A plus lambda B, where A is the position vector of a point on the line and B is the direction vector. So in this case, our line is passing through the points A and B, so I can use AB as my direction vector. So we need to find what AB is. AB is going to be OB minus OA, and AB is equal to OB is 5i plus j plus 6k minus OA, so minus the 2i plus 4k. So AB is equal to, that's 5i plus j plus 6k. Expand the bracket, so minus 2i minus 4k. AB is equal to 5i minus 2i, which is 3i. Then we've got plus the j. Then we've got 6k minus 4k, which is plus 2k. So this is the direction vector of our line. In terms of points that lie on the line, i.e. for this A part, we can use either OA or OB because those are position vectors of points on the line. Doesn't matter which one you choose. So let's use OA. So we can say that R is equal to the position vector of A, which is 2i plus 4k, plus lambda, that's just some variable. Don't worry too much about it. You can put any letter you wish. And then B is the direction. The direction vector is AB, so 3i plus j plus 2k. And that is our final answer. Now we're told that line L2 has equation R is equal to, actually just going to write it in vector notation. So 2i plus j plus 5k plus mu times 1, 2, 3. That's the direction. And I'll also just write L1, which is this line that we have there in column notation, column vector. So 2, there's no j component, so that's 0, and that's 4, plus lambda, and so that's 3, 1, 2. Okay. And then the part B says that show that line L1 and L2 do not intersect. Okay. So what we're going to do is we want to initially solve these equations simultaneously. And you see that we'll get a set of 3 equations. We'll use 2 of the equations to find what lambda and mu are. And then we'll test whether those values of lambda and mu satisfy the third unused equation. If they do satisfy the third unused equation, then it means our lines intersect. If they don't satisfy that third equation, our lines do not intersect. Do not worry if the big picture does not make sense. We'll go through it step by step. So the first thing that we want to do is to write the parametric equations, right? And what that means is that I can break this line down to the x, y, and z component. If I want the x component, it's going to be 2 plus mu times 1. So 2 plus mu times 1. If I want the y component, it's going to be 1 plus mu times 2. So 1 plus 2 mu. If I want the z component, it's going to be 5 plus mu times 3. So 5 plus 3 mu. This is called the parametric form, or your parametric equations of this line. It's another way of expressing the equation of a line. And we want to do the same for L1. So we want the x, y, and z components. So x is 2 plus lambda times 3, so 2 plus 3 lambda. Y is 0 plus lambda times 1, so just lambda. And z is going to be 4 plus lambda times 2 plus 2 lambda. Okay, perfect. And now we just want to equate these parametric equations together. So put the x's, take the x's and equate them, take the y's and equate them, take the z's and equate them. So x, that becomes 2 plus mu is equal to 2 plus 3 lambda. And then the y's, 1 plus 2 mu is equal to lambda. The z's, 5 plus 3 mu is equal to 4 plus 2 lambda. Okay. And I'm just going to label this equation 1, equation 2, equation 3. What we want to do is to use the first 2 equations to solve for lambda and mu. Once we have lambda and mu, we're going to substitute our values for lambda and mu into the third equation. And if the left-hand side of that equation is equal to the right-hand side of that equation, then that means our lines are satisfied, all 3 equations are satisfied, and therefore the lines intersect. But if the left and the right are not equal, then our lines are not, then rather our lines do not intersect, because not all 3 equations are satisfied. So using equation 2, we know that lambda is equal to 1 plus 2 mu. And I'm going to substitute this into equation 1. So using equation 1, I have that 2 plus mu is equal to 2 plus 3 lambda, but I know lambda is 1 plus 2 mu. So let's simplify. We've got 2 plus mu is equal to 2 plus 3 times 1, that's 3. 3 times 2 mu, that's 6 mu. So 2 plus mu is equal to 2 plus 3, that's 5, plus 6 mu. And then let's make mu subject of the formula. So move this to that side. You've got 6 mu minus mu gives us 5 mu. And then we've got 2 minus 5 there. So 5 mu is equal to negative 3. Mu has to be negative 3/5. So we know that mu is negative 3/5. We can find lambda using equation 2. Lambda has to be 1 plus 2 times mu, so 2 times negative 3/5. So lambda is 1 plus 2 times negative 3/5, which is equal to negative 1/5. Okay. So now that we know mu and lambda, right, we're saying lambda is equal to negative 1/5. We need to substitute these values of lambda and mu that we have into the third equation. So let's do that. So using equation 3, we're saying 5 plus 3 mu, mu is negative 3/5. And we're checking if this is equal to 4 plus 2 times lambda, lambda being negative 1/5. So let's simplify the left-hand side. This is 5 plus 3 times negative 3/5. That gives us 16/5, or 3.2. And is that equal to the right-hand side? So I've got 4 plus 2 times negative 1/5. We get 3.6 on the right-hand side. So clearly the left and the right side are not equal. So the third equation is not satisfied. So the lines do not intersect. So we can say that not all three lines, not all three equations are satisfied. Equations are satisfied. So the lines do not intersect. And that is our final answer. Now the part C says, find the acute angle between the directions of line L1 and L2. Okay, so what are the directions? I'll just use D1 to denote the direction of line L1. So the direction vector of line, this one's L2. L1, the direction vector of line L1 is 3, 1, 2. So 3, 1, 2. And we want the direction of line 2. So that's the 1, 2, 3. That's the 1, 2, 3. If we want the angle between these two lines, we can use the formula that says cos theta is equal to the dot product of the two vectors divided by the product of their moduli. Right? So we first need to find their dot product, then find the modulus of each vector and multiply. So we'll start with the dot product of our 3, 1, 2 dot 1, 2, 3. So that's 3 times 1, 3, plus 1 times 2, 2, plus 2 times 3, 6. So 3 plus 2, 5, plus 6, 11. And now find the modulus of 3, 1, 2, which is the square root of 3 squared plus 1 squared plus 2 squared. So that is the square root of 3 squared plus 1 squared plus 2 squared, which is root 14. And now the modulus of 1, 2, 3, which should be the same. The square root of 1 squared plus 2 squared plus 3 squared, which is root 14. And so now if we substitute into our formula there, cos theta is equal to the dot product, which is 11, divided by the product of their moduli, so root 14 times root 14. So you've got theta is equal to arc cos of 11 over root 14 times root 14. Root 14 times root 14 is just 14. So theta is arc cos of 11 over 14. And it doesn't matter whether you're in degrees or in radians since they haven't specified. I'm in degrees and I get 38.2 degrees. And it makes sense because they asked for the acute angle. Acute means between 0 and 90. So that's the angle between the directions. Question number 9. A constant a is such that the integral from 1 to a of 6x ln x dx is equal to 4. Part A says show that a is equal to the exponential of 1 over 6 times 5 over a squared plus 3, okay, where exponential of x is equal to e to the x. So we need to integrate, and the idea will be once we integrate, we're going to end up with some equation in terms of a, and we need to manipulate that to get to the desired result. So for now, I'm just going to ignore the limits, and I want us to integrate 6x ln x dx. Right, so for this, we're going to have to integrate by parts. But we need to figure out what u is going to be and what dv dx is going to be. For that, we use late. And in this case, L represents logarithms, A represents algebra, T represents trig, and E is your exponentials. So in this case, we've got algebra and logarithms. So whatever is higher up on the list is what you choose as your U. So we've got ln x, which is a logarithm, so that has to be U. So use ln x, and dv has to be 6x. So du dx is going to be equal to, if you differentiate ln x, you get 1 over x. And if you integrate 6x, you're going to get 6x squared over 2, which is 3x squared. And now we're going to use the formula for integration by parts, which says that the integral of u dv dx is equal to uv minus the integral of v du dx. So in our case, the integral of u dv, so that's 6x ln x dx, is equal to uv, so 3x squared ln x, minus the integral of v du, so 3x squared times 1 over x, 3x squared times 1 over x dx. We can simplify this, right? Because x squared over x, that cancels out, and you just end up with 3x. And so that means there we're just integrating 3x with respect to x. So we can simplify this and say that the integral of 6x ln x dx is equal to 3x squared ln x minus 3x add 1 to the power 2 divided by the new power 2. Technically, we should add a c here because there are no limits, right? But we're about to bring back the limits, so it doesn't really matter. So this is the result you get when you integrate 6x ln x. I'm going to put that in brackets and say 3x squared ln x minus 3x squared over 2 we were dealing with the limits from 1 to a, and we were saying that this has to be equal to 4. We just substitute in our limits. So we'll start with the upper limit, which is the a. So it becomes 3a squared ln a minus 3a squared over 2 minus, now we do the lower limit, which is 3 times 1 squared ln 1 minus 3 times 1 squared over 2, and this is all equal to 4. So that's 3a squared ln a minus 3a squared over 2 minus ln 1 is 0, so this whole thing becomes 0. Then we've got minus 3 over 2. And this is equal to 4. So that is 3a squared ln a minus 3a squared over 2 plus 3 over 2 is equal to 4. And so that's 3a squared ln a minus 3a squared over 2. I'm moving the 3 over 2 that side. So I've got 4 minus 3 over 2, which is 5 over 2. And I think I'm just going to multiply through by 2 to get rid of the denominators. So we'd end up with 6a squared ln a minus 3a squared is equal to 5. And now we just have to figure out what can we do to get to our desired result. All right, that is our desired outcome. What can we do? Okay. So the first thing that I notice is this a squared that's there by itself. I can see that I've got 2a squareds here. So I'm tempted to factor out an a squared, right? And I think we're going to do that. And it's dividing, okay. The a squared is dividing a 5. So we could factor out a squared. And then we've got 6 ln a minus 3 is equal to 5. And I can tell that my a squared there is dividing a 5, so I can divide both sides by a squared, so that I've got 6 ln a minus 3 is equal to 5 over a squared. And now I can see that I've got this 3 that's adding. I can get that by just moving that there. So I've got 6 ln a is equal to 5 over a squared plus 3. And now I've got this 1 over 6 that's multiplying this whole thing. So I can do that if I just multiply both sides by 1 over 6. So now I have that ln a is equal to 1 over 6, 5 over a squared plus 3. And now I can just apply the exponential function on both sides, and we have arrived. So if you apply e here to this, and you apply e to this, you get that a is equal to the exponential of 1 over 6 times 5 over a squared plus 3, and that is our final answer. This paper is long and tedious. Part B says verify by calculation that a lies between 2 and 2.1. Okay, so what you're going to do is we want to create a function called f of a, which is going to put everything on one side. So I'll move the a to the right hand side, and then I'm going to call that f of a. So the exponential of 1 over 6 times 5 over a squared plus 3, and then the a moves to the right, so it subtracts. And what we want to do is evaluate f of 2 and f of 2.1. If we get a change in sign, then that means a has to lie between 2 and 2.1. So f of 2 is equal to the exponential of, that's 1 over 6 times 5 over 2 squared plus 3, minus, that's 2, punch this into the calculator, e to the 1 over 6 times 5 over 2 squared plus 3. Be careful with the brackets there. And so you get plus 0.0306. What about f of 2.1? This is the exponential of 1 over 6 times 5 over 2.1 squared plus 3 minus the 2.1. So let's punch that into the calculator and we get a negative 0.108. So clearly there's a change in sign. So we can say that, therefore, since there is a change in sign, A, which is our root, A lies between 2 and 2.1. Part C says use an iterative formula based on the equation in part A to determine A correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay. So the equation from A is equal to the exponential of 1 over 6 times 5 over A squared plus 3. To convert this to an iterative formula, I just need to add n plus 1 there and n. Okay. And we need to come up with our initial value, which we'll call A0 or A0. And for initial value, I'm going to use 2. You can use 2.1. It works just as well. A0 is 2. We need to evaluate A1. So A1 is going to be the exponential of 1 over 6 times 5 over A squared n. So that's going to be A squared 0, or rather A0 squared, which means we need to take that 2 squared plus 3 and punch this into the calculator. This is the exponential of 1 over 6 times 5 over 2 squared plus 3, and this gives us 2.03. They want the results of each iteration to 4 decimal places, so 0306. 0306, okay. And then we're going to do a 2 exponential of 1 over 6, 5 over. So instead of trying to rewrite this value there, because we want the result of the previous iteration, right? I'm going to use a function on the calculator that stores the result of the previous iteration, and that's the ANS pattern, which you find in most calculators, you find next to your equal sign. So you can use that and say answer squared plus 3, because it stores the result of your previous iteration. So where you initially had your A0, replace with ans, and now just press equals. You get 2.017. We want to 4 decimal places, so it has to be 80. And now don't change anything on your calculator. Press equals. You get 2.0231. And I believe we have our answer because we wanted correct to 2 decimal places. This is 2.02. This is 2.02. Perfect. So therefore A is 2.02, and that is our final answer. Question number 10, part A. Find the quotient and remainder when x cubed plus 5x squared minus 2x minus 15 is divided by x squared minus 3. Right, so we have to do polynomial division. And how this works is that you're going to take the term with the highest power of x in your divisor, and that's the one you're going to use to divide. So in our case, we're going to start off by saying x cubed divided by the x squared, you get x, and then multiply through by the divisor. So x times x squared, you get x cubed. X times negative 3, you get negative 3x. Simplify x cubed minus x cubed, that's 0. Then you've got the 5x squared there. Then we've got negative 2x, negative 3x. So 3x minus 2x, which is x. Then bring down the negative 15. And then divide 5x squared by x squared, you get a 5. So 5 times x squared, that's 5x squared. 5 times negative 3, that's negative 15. And if we simplify this, that's 5x squared minus 5x squared, which is 0. And then we've got x minus 15 minus minus 15. So that's minus 15 plus 15, which is 0. So now that the highest power of x in our dividend is smaller than the highest power of x in our divisor, we can't continue dividing anymore, so we stop. And then whatever we have at the bottom here is our remainder. What we have up top is our quotient. So we can conclude that therefore the quotient is x plus 5, remainder is x. Okay. And I think this will probably be applicable to part B. But basically, if you divide a polynomial by your divisor, this is equal to whatever your quotient is. So I'll call that Q of x plus whatever your remainder is divided by the divisor. So this is another way of expressing your polynomial if you divide it. So I know that my polynomial divided by the divisor can be written as the quotient plus the remainder over the divider. Sometimes you might actually find it more useful to multiply through by the divisor so that you've got p of x is q of x, d of x plus r of x. So quotient times divisor plus the remainder. Okay, but in our case for part B, because I have insider information, I know that this first form is more relevant to us. And so what that means is that our polynomial here is x cubed plus 5x squared minus 2x minus 15, and it's being divided by x squared minus 3. So this has to be equal to our quotient, which is the x plus 5, plus the remainder, which is the x, over the divisor, which is the x squared minus 3. So we'll come back to this when we talk about part B. Part B. The variables x and y satisfy the differential equation dy dx is equal to, that's x cubed plus 5x squared minus 2x minus 15 all over, this is 6y times x squared minus 3. It is given that y is equal to 2 when x is equal to 2. Solve the dE to obtain an expression for y squared in terms of x. Alright, so when you've got a differential equation, the first thing to do is to separate your variables so that everything with y is on one side, everything with x is on the other side. So that's what we want to do here. So I'm going to move everything that has y to the left hand side. So on the left, I know I want to keep my dy because it has y, and this dx is going to end up moving to the right, and then this 6y has to move to the left. But notice that our 6y is dividing this side, so when it moves to the left, it has to multiply. So I should have 6y here is equal to, everything else on the right should stay, x cubed plus 5x squared minus 2x minus 15. And this is all over x squared minus 3. And I hope this result here looks familiar. And then the dx moves to the right. That's dx. Once you've separated your variables, you want to integrate both sides. Okay. If we integrate 6y with respect to y, that's going to be 6y, add 1 to the power, that's 2, divide by the new power, that's 2. Let's add our constant of integration. And then for the right-hand side, so remember the result we talked about earlier, right? And if you just happen to skip part A and jump straight to part B, this is the result we're going to use. Watch part A first, if you didn't watch part A. But we can't, well, we can if you really wanted to integrate this, but it's very difficult to integrate this directly. So we would rather integrate x plus 5 plus x over x squared minus 3. So we're going to rewrite this as the integral of x plus 5 plus x over x squared minus 3. And this is all with respect to x. Okay. So left hand side, that is 3y squared plus c. And then I want to actually separate this integral sign because I want to do this separately. We'll integrate the x plus 5 by itself, and then we're going to integrate x over x squared minus 3 dx by itself. So I'm sure integrating x plus 5 should not be a challenge, I hope. What we want to focus on is integrating x over x squared minus 3 dx. The result we want to use is the result k, the integral of f prime of x over f of x with respect to x is equal to k, the natural logarithm of f of x. So what this is saying is that if I differentiate my denominator and find that my numerator is the derivative of my denominator multiplied by some constant, then this just integrates to k ln f of x. So in our case, if I differentiate x squared minus 3, I'm going to get a 2x, which is not quite my numerator, but it's close. So we can actually force it to be, right? So I can say if I differentiate x squared minus 3, I get 2x. So I know that I need to have 2x on my numerator. But we didn't originally have 2x. So what we can do is multiply by half to cancel out that 2. Because half times 2 gives me the initial thing that I had, which is just x on the numerator. But now we have it in this form of k f prime of x over f of x with respect to x. Because if you differentiate x squared minus 3, now you get 2x, which is the derivative of our denominator. And so using the result on the right, we can say that this becomes half, which is our k, ln of f of x. F of x is the x squared minus 3. And so coming back here, we have that 3y squared plus c is equal to the integral of x plus 5. So integrate the x, raise or add 1 to 1. You get 2 divided by 2 plus 5 becomes 5x. And then the integral of x over x squared minus 3 dx, we found that out to be half ln x squared minus 3. Okay, perfect. So that's our result there. And remember, we were told that when y is equal to 2, x is equal to 2. So we can use that information to find our constant of integration. So that becomes 3 times 2 squared plus c is equal to 2 squared over 2 plus 5 times 2 plus half the natural logarithm of 2 squared minus 3. 3 times 2 squared, so that's 3 times 4, 12 plus c is equal to 2 squared over 2 which is just 2 plus 10. So I'll write that as 12. And then half ln, as 4 minus 3, so half ln 1. Ln 1, we know that that is equal to 0. So this is plus 0. So you end up with C being 12 minus 12. So C just ends up being 0. And so now if we come back to this here, we have that 3y squared plus 0 is equal to x squared over 2 plus 5x plus a half ln x squared minus 3. And if you read the question again, it says solve the DE to obtain an expression for y squared in terms of x. So that means you have to make y squared subject of the formula. And to do that, we just need to multiply through by 1/3 or divide through by 3. So y squared becomes x squared over 2 divided by 3, which is x squared over 6. Then divide 5x by 3. Then divide a half by 3, you get a sixth ln x squared minus 3. And that is the solution to our differential equation. Number 11. Number 11. The diagram shows the curve y is equal to cosine of x times the square root of sine of 2x. For x is between 0 and a half pi. The curve has a maximum point at M where x is equal to a. Part A. Find the exact value of a. Okay. So M is a maximum point, stationary point. So we know that dy dx is 0. So that means we first have to find what our dy dx is. So to do that, we need to differentiate our y is equal to cos x. I'll rewrite sine 2x as sine to the half 2x. I meant to say sine or root sine 2x as sine to the half 2x, but that's fine. Dy dx, we're going to use the product rule here. So hold the cosine of x, differentiate the sine half of 2x. Let's actually do that on the sine. We want to differentiate sine half 2x. So start with the outer function. Let's ignore the notation, actually. It makes things a lot more complicated. We've got sine of 2x, and this is all being raised to the power half. So let's start with the outer function. Bring down the half, sine 2x. Subtract 1 from the power, so half minus 1, you get minus half. Multiplied by, there's two inner functions here, so be careful. Multiplied by this inner function, so sine, what do you get when you differentiate sine? You get cosine of 2x. Multiplied by, there's another inner function, which is the 2x. What do you get when you differentiate 2x? You get a 2. Okay, probably put brackets here. And so if we simplify this, we've got a half multiplying the 2, so that would cancel out. And so you end up with cosine of 2x multiplying sine to the negative half of 2x. Okay, so that's our result there. Got cos 2x sine to the negative half 2x plus, now we're going to hold the sine to the half 2x, and we want to differentiate the cosine of x. So if you differentiate cosine of x, you're going to get negative sine of x. this is multiplying negative sine of x. All right, perfect. That is our dy dx. It does not look nice at all. What is the best way to simplify this? Okay, let's just rewrite this as dy dx is equal to, all right, cosine of 2x cos x sine to the negative half of 2x minus our sine x and then sine to the half of 2x. And because we are interested in a stationary point, we know that dy dx has to be 0. So this whole thing has to be equal to 0. And now we need to find a way to obviously solve our equation here. So I want to rewrite this part with a positive power. So I'm going to take it down to the denominator. So I'm going to have cosine of 2x multiplied by cos x. And this is being divided by sine. So that power becomes positive sine to the half 2x. Then minus our sine x, sine to the half 2x. And this is all equal to 0. And I think the next step, what makes sense is to just get rid of the denominator, right? So that means we have to multiply through by the sine a half 2x. So I'm multiplying this whole thing. And technically we're also doing it on this side, but we're multiplying by 0, so it will make a difference. So that gets rid of our denominator on the first term. So we've got cos 2x, cos x. And then on the second term, we've got negative sine x. And then I've got sine to the half 2x, right, from here. And then it's also being multiplied by that sine a half. So from laws of indices, if you've got a to the m times a to the n, it becomes a to the m plus n. Our bases are the same, so it means that I have to do sine half plus a half, which is just 1, 2x. So I just end up with sine of 2x. Right, so that there becomes sine of 2x. And magically that half power that was bothering us is gone. Right, so this looks much nicer. And how do we want to go about this? I think the first thing is just using the double angle formula for sine, right? This is identical to 2 sine x cos x from the MF19, so that we can rewrite this. So I'd end up with cos 2x cos x minus sine x, and this is being multiplied by 2 sine x cos x. This is all equal to 0. So that's cosine of 2x cos x. Then here I've got sine x times sine x, so I've got 2 sine squared x cosine of x is equal to 0. And I'm just holding off expanding cosine of 2x because I want to see which identity for cosine of 2x makes sense, because remember I've got 3 options. And so I can see a cos in both terms, so I'm going to factor that out. Cosine of x times cos 2x minus 2 sine squared x. Now I see that my expression has sine squared x, so it makes sense for me to use the cosine 2x identity that only has sine squared x. So I'll use cosine of 2x is identical to 1 minus 2 sine squared x. So cos x times cosine of 2x, that's 1 minus 2 sine squared x, minus this 2 sine squared x. and this is all equal to 0. And so we've got cos x, and this is being multiplied by 1 minus 4 sine squared x, and this is equal to 0. So we have that either cosine of x is 0, or that this bracket here is 0. Okay, and we have to solve the two equations. So I've got cos is 0, so x has to be arc cos of 0. And be careful, arc cos of 0 is not equal to 0, it is equal to, in radians, it's pi over 2. Okay, pi over 2, and if you look at our diagram, pi over 2 would be right here, so that's not the solution we're interested in. We want A. So that's definitely not our solution. Let's solve the other equation. So this becomes 4 sine squared x is 1. And so sine squared x has to be a quarter. And so if you take the square root on both sides, sine x is, remember, plus or minus root a quarter. Root a quarter is 1 over 2. So plus minus 1 over 2. And now we've got two equations. Either sine x is negative 1 over 2, or sine x is positive 1 over 2. And so when sine x is negative 1 over 2, I've got x sine of negative 1 over 2. X has to be, make sure your calculator is in radians. This is x sine of negative 1 over 2. And so that gives us negative 1 over 6 pi, which is not what we're interested in. Just going to solve the other one to see. This one should give us positive a 6 pi, which should be within our interval. Right. Let's double check that. 1 over 6 pi. Yes, 1 over 6 pi is less than a half pi, so it makes sense. So we can conclude that, therefore, A has to be 1 over 6 pi, because this is the x coordinate when dy dx is 0, which is what A is representing. All right. So that's the part A of this question. And then part B, now they're just having fun. The region enclosed between, let's go to the diagram, or let's copy the diagram. Control C, V. Okay. So the region enclosed between the x-axis and the curve is rotated through 2 pi radians about the x-axis. Let's see if we can make that happen. So whenever you're doing a volume of revolution question, you want to see if you can just get some sort of visual representation of the volume, right? So in this case, first reflect in the x-axis, reflect your curve. So something like that. And I mean, if I take a point here, what they're saying is if I take this point and I rotate it 360 degrees about the x-axis, this is what's happening on every point on this shape. So we've got some weird shape, sort of looks like a tulip. If you know what a tulip is, that vegetable, you can think of it as a tulip, or some weirdly shaped onion. That's what you're looking at here, but it's on its side, right? So that's the three-dimensional volume of revolution that they're talking about here. So they're saying find the exact volume of the solid generated. So, I mean, this is a nasty question. One, because you don't really expect to see volume of revolution in pure 3. It's mainly a pure 1 concept. But again, when you do A2 maths, your AS knowledge is assumed. So that's unfortunate. And then 2, we are going to have to integrate some crazy function. All right, so volume of revolution, your formula is pi, the integral from what are our limits for going 0 and half pi. So 0 and half pi. And we are integrating. The formula says y squared dx. So we need to find an expression for y squared in terms of x. So if y is equal to this, what is y squared equal to? Y squared has to be cosine of x root sine 2x whole squared. So let's distribute the power 2. So square the cos squared x, and then square the root sine 2x. So that gives you sine 2x. So what that means is that our volume becomes pi, the integral from 0 to half pi multiplied by y squared, which is cosine squared x sine 2x dx. This is what we have to integrate. So there are two ways of doing this. One of the ways would be to use a substitution, but the faster way of doing this is quite difficult to see, and also quite a niche technique of integration or method. So if you've got the integral, let's put it in red, because why not? If you've got the integral of f prime of x multiplied by f of x with respect to x, then the result becomes f of x squared, right? I'll put that in brackets, f of x squared divided by 2 plus, of course, your constant of integration if you want to be by the book. All right, so we have to, in this case, we do have the form f prime of x, f of x, but let's actually show that. If we focus on expanding sine 2x, we know that sine 2x is identical to 2 sine x cos x, right? That means I can rewrite this as cos squared x times 2 sine x cos x. And this is with respect to x. If you differentiate cos squared x, if we differentiate cos squared x, I'll write it the other way. If we differentiate cos x squared, right, if you differentiate this, you first do the outer function, so bring down the power. You've got 2 cosine of x, subtract 1 from the power, so it's 1. And then you differentiate the inner function, so you differentiate cos, which becomes negative sine x. And so that means the differential of cos squared x is negative 2 sine x cos x, which is very close to what we have here, right? We're saying that if f of x is cos squared x, then what we want as our f prime of x has to be negative 2 sine x cos x. So we need a negative sign there. If we introduce that negative sign, I can just put a negative and that would act as a constant, right? I can put a negative outside so that it cancels out this negative. And now we've got f prime of x multiplying our f of x with respect to x. And so what this means is that the result of this integral becomes, you've still got this negative that's hanging outside, got that negative, and it has to be f of x. Our f of x is the cos squared x. And the result says we have to square that. And this is being divided by 2, cos plus a constant of integration. So if you simplify this, this is negative cosine 2 plus 2 times 2, not 2 plus 2. That's 4x over 2 plus c. So this here is the result that you get when you integrate cosine squared x times 2 sine x cos x, or if we want to write it as sine 2x, with respect to x. This is the result that you get. But now let's bring back our pi and our limits. So I know that I had a pi outside here, and I'm going to take this negative sign outside as well, so that I've got cos to the 4x over 2, and our limits were from 0 to a half pi. 0 to a half pi. And now we substitute in our limits. Start with the upper limit. So cos to the 4 of half pi over 2 minus cos to the 4 of 0 over 2. Punch that into our calculator. Remember, you can't punch in cos to the 4x in your calculator. So you do cos x all to the power 4. So I'm going to do, this is cosine of pi over 2. And then I'm going to raise that to the power 4 and divide it by 2. I get a 0. And then I'm going to do minus. I've got cos 0 raised to the power 4 over 2. I get a half. And so if we simplify this, this has to be 1 over 2 pi. And that there would be your final answer. I'll admit this is a very niche integration result, which most people may or may not know. I don't know. And even then, it's quite difficult to spot in this scenario. The alternative would have been to use a substitution, like let u equal to, what would have worked here? Let u equal to cosine of x should have worked. I mean, it would be long, but it would have worked. And it's a more obvious approach, I guess. But yeah, that's it for this paper. I hope you found this breakdown useful. If you did, please let me know in the comments down below, and let me know what other past papers you'd like to see me break down. Otherwise, like the video, subscribe, and I'll see you next time.